We are on Unit 3, Chemical Bonding, and you'll see that each unit scaffolds from another from the previous unit, so we're going to see a lot of concepts that we've learned from Unit 2, which was on periodic trends. So take some time, read um, this introduction, as well as it moves us through the storyline of what will occur through this whole unit. So please take a little time to read the beginning and fill in your blanks. As always, these are key words that I would like to highlight as we go through this unit. So, this is a great, I always start off every year with this chart right here, and it's all the different types of bonds in chemistry. We're going to learn about covalent bonding, and my abbreviation is C, ionic bonding, I, metallic bonding, M, and then also something called covalent network, which is really related to covalent. However, the network of bonds is what differs covalent from covalent network. You are to fill out your chart. You should fill out all the items that you see blank to help you to understand what a metal or a covalent bond is made up of, an ionic bond is made up of, versus a covalent network and a metallic. The nature of bonding, covalent is about sharing electrons, whereas ionic is about transferring electrons. Metallic is about delocalized mobile electrons that are surrounding the cation of that metal. Covalent network is still sharing, but sharing in a very intricate, complex manner compared to just simple sharing between atoms. Forces of attraction. One of the key ideas in covalent is that there are intramolecular forces, but there are also intermolecular forces. And inter means between molecules, intra is within. So there's bonding that's occurring within the atom or the molecule, and there's also forces of attraction between particles. Ionic bonding has only intramolecular forces, and those intramolecular forces are really the bonding that's between or that's within the structure of an ionic compound right here that is between the cations and the anions. So it's a intramolecular force. Metallic bonding is also an intramolecular force, and that's why the forces of attraction are increasing as you go this way. So this is increasing forces of attraction. So the strongest one is in fact the metallic or the covalent network. And if you look at the wording, it tells you very much that's the strongest one. It says very strong electrostatic attraction within a network of atoms bonded via sharing of electrons. So you can see the progression of strength. Now, the reason why covalent compounds are weakest because they're guided by these intermolecular forces, which are weaker than intra. So that's what makes covalent compounds extra special, is because they have these intermolecular forces. Units. Covalent, we have different words to represent these units of substances. Covalent compounds are called molecules. Ionic compounds are called formula units. So this is a formula unit of sodium chloride. Metal ion is what we call for metals. And then formula unit is also be used for covalent network. Loose structure. So you'll see some dot structures as we go through this. Electron dots will bond in order to fill energy levels, as we stated. So bonding will take place in order to fill energy levels. As we see here in ionic bonding, sodium will lose one electron, having a +1 charge, and upon losing one, sodium will have a full second energy level. Sodium is going to transfer it to chlorine, which has 7 valence electrons, but upon gaining an electron from sodium. Chlorine now has a -1 charge, and now sodium has a full third energy level, and that's the 8, the octet you see for chlorine. Although you don't see the octet for sodium, sodium has an octet because sodium, the second energy level is full, which means there's 8 on the second energy level upon losing its one valence electron. Magnesium here, when you show her the Lewis structure, all you're showing is the electrons delocalized. So Mrs. No is going to show electrons moving by arrows, electrons moving about around the magnesium ion, that is. And then last but not least, the covalent network. The Lewis dot is just really the bonding that takes place. It's very much the sharing, the same sharing, but notice it's a continuous sharing. So how I would represent the continuity of that sharing is this. I would literally draw more bonds, and there's continuous sharing as we see the bonds take place. Okay, so there's continuity on that. Now we go to macrostructure. It's actually the properties that we all will see are really based on many atoms or many molecules of a covalent compound, or many covalent formula units of an ionic compound, or many metal cation of a metal bonded together. So there's many, and that's what we call a macrostructure or a bulk structure, and meaning many big amounts of atoms. And so here is the covalent network solid that you see for covalent network and metallic bonding, ionic bonding, as well as covalent. Notice in covalent, I'm always really stressing the intermolecular forces versus the intra. So here we have the intramolecular forces versus the intermolecular forces. Okay, so this is the macrostructure of each types of bonds, noticing that the covalent distinctly have intermolecular forces aside from the intra. Covalent network in this example, graphite, actually has some intermolecular forces between each plane, but this is where this is where the bonding is occurring that I'm emphasizing for a graphite molecule. It's the intramolecular forces that are engaged right here, not so much the inter in graphite, okay? Now, these bulk properties, the bonding that takes place in all these substances really dictates all of these different properties that you see, whether it's melting point, boiling point, whether it's conductivity, brittleness, vapor pressure, surface tension, or states of matter. So all of these properties of bonding, as you see, will lead to the different high melting points or low melting points that you see in covalent. High in covalent network, low in covalent. And we see that actually progressing with the same trend that you see as far as the forces of attraction. So as you go from left to right, you're increasing in the forces of attraction. And that's why you're seeing that progression of boiling point increasing as you go from left to right here. We will talk about covalent compounds and polar substances versus nonpolar, and how they have certain IMF forces, intermolecular forces, the type of intermolecular forces. And this will actually dictate the strength of attraction. And likewise, you're also going to see them ordered. Polar substances are stronger forces, so they have a higher force, whereas nonpolar substances have lower force. So hopefully you can see that. Now, ions, when it comes to conductivity, we're looking for free ions. Since covalent compounds are bonded through sharing of electrons, you don't see charge ions. They're sharing electrons, you will not see charge ions. Whereas ionic compounds, you're seeing charge ions result from the electrons after the electrons transfer between the metal and the nonmetal. the cation to the anion. And so you're actually going to see some conductivity because there's free ions. As long as there's free ions, we see conductivity. Now, metals also have that metal cation that is in a sea of delocalized electrons, so metals are very good conductors. That's why metals are everywhere for conductivity purposes. If you open and cut up a wire, you will see metals because that's what metals are used for, conducting electricity. Metallic or covalent network has little to no conductivity because they're sharing, just like covalent compounds. Sharing leads to no free ions, so there's little to none. Brittle characteristic. We'll see brittleness as we go through some of the substances, specifically ionic. Ionic compounds are brittle, but we'll see it when we get to ionic bonding. Vapor pressure. Vapor pressure essentially is the vapor state. And how I think of vapor pressure, class, is I hope you draw this. I think of basically a flask. In the flask is a liquid, and some of that liquid will vaporize. And so this is the vapor state. And whether, depending on the strength of attraction as far as the liquid, when the substances are in liquid form, that will dictate how much vapor is going to form. If there's stronger forces down here, the stronger the force down here, those particles are held tightly together, preventing them from easily becoming a vapor. So you'll notice once again, the substances here, covalent compounds have intermolecular forces, which are weak attractive forces, and then that's why they tend to have a higher vapor state, because the weaker the intermolecular forces, the weaker the attraction here, the higher the vapor state. That's why all these are low or none. Some of them do not have any vaporization related to it. Diamond is a perfect example of not vaporizing, and it has covalent network. You wouldn't want your diamond ring the diamond in your diamond ring to actually vaporize. Surface tension is a characteristic where you're looking at how tight the bonds are. However tight those bonds are on the surface of this drop of liquid will cause the concavity of this drop to be more um, more more concave or less concave. So concavity, the degree of concavity will determine that surface tension. Now, the stronger the attractive forces between those particles, the more concavity you'll see. So the more rounded that drop will be versus a less rounded. And notice how covalent compounds have low vapor surface tension oftentimes, versus all of these substances will have higher surface tension if you looked at it in the liquid state. So we're looking at surface tension of liquids, a drop of liquid, each of these liquids. States of matter. This forces of attraction, the stronger the force of attraction, the stronger those particles will hold together, making them more like a solid, or covalent compounds, which vary. And usually they are gases or liquid more so at room temperature. Some of them are solids. If they're solids, they tend to melt very readily, or they tend to vaporize if they're solids. Okay. Let's go into intramolecular forces and versus inter. There's an error here. It's supposed to say intermolecular forces. Let me go ahead and edit that. And rewrite it to make sure. Covalent compounds, as we suggested before, has intramolecular Intermolecular forces, which are the bonds that occur between the oxygen hydrogens. They also have intermolecular forces, which are something called, they're actually called hydrogen bonding in water. So intra are called covalent bonds where atoms are sharing together. Inter are London dispersion, dipole-dipole, as well as hydrogen bonding and Ion-Dipole forces. And they're in between the forces that are between the substances. Now, ionic has only intra, as we stated earlier, and that's the bond between the cations and the anions, the opposite charge ions here. Metallic bonding has intra, and in this intra, you're looking at the cation, metal cation, and its delocalized electron right here. So there's an opposite attraction between the negative charged electron and the positive charged ion that is in metals. And so these are the electrons that you're seeing that are delocalized in each of these from these cation metals that you see here. Okay. And this is an intra, attraction between opposite charged cation and their delocalized electrons. Now we get to covalent network. It's a network of atoms. Notice how one bond occurs continuously onto another bond until they get cut off. So this is a continuous network of atoms, and that's why this is an intramolecular bond force that's occurring. But the atoms are still sharing, but they're sharing continuously. So in a network of atoms. Let's go on to bond type and electronegativity. The bond type, we're going to use these electronegativity values to determine the bond type. And if the difference in the electronegativity between the two atoms that are bonded is between 0 and 0.3, we call that bond type a nonpolar covalent. Usually it's between two nonmetals. If the difference lies between 0.3 and 1.7, we call that a polar covalent bond, and it's between two nonmetals often. Covalent compounds are bonded between two nonmetals. Ionic is metal and nonmetal, and thus if the higher the electronegativity difference between the two atoms, and oftentimes you'll see it from one atom on this side, which is a metal, and the other another atom on this side, which is a nonmetal, and that difference is going to be a large difference. That large difference makes that bond ionic. Okay, so we're going to look at example 1. We're literally going to calculate the difference and see the bond between nitrogen and iron. So I look up iron and it's 1.8. And so I take 1.8 and then I look at nitrogen, which is up here 3.0. So I'm going to take the difference between nitrogen and iron. So the difference, and I take the absolute value of that difference, okay, class? So please make sure you're looking at absolute values. That's your absolute value sign. And so it's 1.2, right? So the answer is 1.2. And now, if the difference is 1.2, we know the bond type is a polar covalent bond. So we equate that to what is called a covalent polar covalent bond. Sorry, I might have said covalent network. It's supposed to be polar covalent bond. So now we go to the next one, oxygen and hydrogen. Oxygen's electronegativity value is 3.5 minus hydrogen, which is 2.1. You take the difference and you get a value of 1.4. With 1.4, we're going to say it's polar covalent. Let's look at sodium chloride. Sodium has a value of 0.9. Chlorine has a value of 3.0. So 3.0 minus 0.9. I don't need to have an absolute value if I know that I'm always going to subtract the smaller value from the larger. And so this is 2.1, which means it's ionic. And sodium chloride is an ionic bond. Now if you have two of the same elements, 2.5 minus 2.5, you definitely know that is 0, net difference, and so this is a nonpolar covalent. And I like to write the word covalent in. You're going, why do we have to write it all the time? Because the word polar and nonpolar only applies to covalent compounds. Now we go to calcium and phosphorus. By the way, you should be pausing if you find yourself being able to understand how to calculate and understand the bond type from that, looking at this chart. So please pause if you find yourself being able to work ahead without me showing the work. So phosphorus is 2.1, calcium is 1.0. Take the difference, it's 1.1, and it looks like polar covalent bond. Okay, check your answers on the bottom. Hopefully you can do that, making sure that you understand the concept of bond type and using the electronegativity difference to calculate the bond type. So let's start off with ionic bonding. In an ionic bond, what we're seeing is electrons are transferred from the metal cation, which has a low Zeph and lots of energy levels, which means that metal cation would like to lose electrons to the nonmetal anion, which would be gaining because nonmetals tend to have a high Zeph with low energy levels, which means its force of attraction is increased. So lattice energy is ionic compounds have what is called a lattice structure. And the reason why the word lattice is used, it's a repeating regular pattern of cations and anions. So you'll see a structure that I'll show you later on when we look at characteristics of ionic bonding. Structures, repeated patterns of cations, anions, and anions, and it's always repeating in a three-dimensional structure. A single ionic unit, called a formula unit, is always electrically neutral. And what that means is it's the simplest whole number ratio between the two ions that make up that substance. We will be forming electrically neutral ionic compounds soon enough. Ions are strongly bonded, so they have high melting points and boiling points. They tend to be a solid at room temperature because they're bonded through, recall, the intramolecular forces. That's why you see them, ionic compounds, solids at room temperature. They do not conduct electricity unless they've been melted. They've melted, so they're in the molten state, so they're in the liquid state. They're good conductors of electricity because their ions are freed up. And when you have freed up ions, that's when when a substance is conductive. When they're solids, they're fixed and locked into place, and so that's why they don't conduct electricity. Ionic compounds are oftentimes soluble in water. We're going to learn that water is polar, and that polarity, that very polarity, so it's polar covalent, is going to allow water to interact with ions through opposite charges. The charge of the ion will definitely orient themselves in a way with water surrounding it, in such a way that the opposite charges are attracted between the ion and the water. And we call that IDF, Ion-Dipole Forces. Ionic compounds are also, their lattice energy, which is the energy in the formation of ionic solid from gaseous ions, that's the definition of lattice energy, is usually higher for smaller ions and greater charge as guided by Coulomb's law. In other words, the lattice energy will be high if you have a smaller ion with a higher charge. And that really is Coulomb's law, guided by Coulomb's law. Higher lattice energy indicates higher boiling point and melting point. And then the charge has significant impact over the size of the ionic compound. So charge trumps size. Here is an example of KCl and LiCl, and it's asking which of these compounds has the most negative or the largest lattice energy. So if you ignore the negative sign, you actually can look at the magnitude of the lattice energy, and that will tell you which one is the strongest. So which one will be strongest? Well, take a look at these two substances. You'll notice that the potassium ion is bigger, lithium ion is smaller, and that's because lithium ion only has 3 energy levels. Potassium has 3 energy levels, and lithium has 1 energy level after it loses 1 electron. So 1 energy level, 2 energy levels, you can bet on this being larger. If this is potassium being larger, potassium will have a weaker attraction for the chloride ion than lithium, which is smaller. And so the distance and the force is going to be stronger between the ions. So let's make sure we circle that, and the one compound that has the largest lattice energy, and we can certainly use the energy levels. So this is N equals 1. This is N equals 3. Now we go to magnesium oxide and lithium chloride. Now, if you look at them on the periodic table, magnesium's right here, oxide is right here, lithium is right here, and chloride's right here. They're kind of swapped in terms of energy levels. So really, you can't use energy levels per se, but what you can use now is charge. The charge of magnesium is +2. The charge of oxide is -2. These are higher charges than the charge of lithium, which has a +1, and chloride, which has a -1. So higher charges will have higher lattice energy according to Coulomb's law. So we're going to use this, circle this, and we're going to say charge plus, we're going to say +2, -2 is higher charges than +1 and -1 charges. So higher charge. Now go ahead and let's do some example problems as far as what we said earlier, which is we're going to make electrically neutral simple ratios called formula units. So we're going to make a bunch of formula units of these substances, and they have to be neutral, okay? So what I mean by neutral is the charges have to neutralize themselves. That's how you know they are a simple whole formula unit, and the correct simple whole formula unit. So a +1 and a -1 equals KCl, neutral. A +3, as you see here, and a -1 means we're going to need 3 chloride ions. And what that means is Mrs. No is going to literally draw this in so you can see that you're going to need 3 chloride ions, which means the formula is Al1Cl3. And the 3 is on the bottom to show for the 3 chloride ions. Same here when we get to iron with a 3+ charge. The way I what I like to look at when it comes to these common multiple charges is the greatest common multiple between 3 and 6, or 3 and 2, which is 6. And so it looks like I'm going to need another Fe3+, okay, so that's your +6, and then another 2-, and then another 2- in addition to that. That's -6, -6 charge-wise. Notice the charges all neutralize. A +6 neutralizes with a -6. So what's the formula look like? Well, there's 2 irons, 1, 2, 3 oxygens. So the formula is going to be Fe2O3. Okay. Now, if you're getting the hang of this, I would pause and work through the rest of the problems. The answers are on the bottom. I'm just going to do one more with you to make sure you understand. Once again, this is +1 and -2. So the common multiple is 2. So that means I'm going to have another lithium. So I'm going to write in lithium 1 plus. Now, that means lithium 1 plus, +1 and +1 is +2, and then -2 here adds to neutralize a a net charge of 0. So my formula is going to be Li, and there's 2 of them, with an oxide, LiO, or Li2O. Work through the rest, please, and make sure that you get through understanding what all these formulas are. I'm just going to write it in. Once I get the hang of it, I know my common multiple for between cobalt as well as phosphide is 6, so 3 here and 2 here. And then Ag2S. So these are my formulas. Answers on the bottom, so you can also double check. All right, let's get into something called the Sox System. The Sox System is it's a system for naming ionic compounds. And we found out from last unit that elements in the d orbital, the ones right here that are highlighted specifically, have more than one cation. And so they have 2 or more cations. Because of that, we need to use Roman numerals to represent the charge on the cation because there's multiple possibilities. For instance, let's look down here. Iron can be iron 2 plus or iron 3 plus. And because iron can be 2 plus or 3 plus, when it combines with chloride ion here, you'll notice that FeCl2 is formed here, and then FeCl3 is formed here. So now, if I called these two substances iron chloride, how do I know which formula to be writing down? Should I write down FeCl2 or FeCl3? So what you have to do, in addition to writing iron chloride, you are to write the Roman numeral of that substance. So the Roman numeral is 2 plus, just like this Roman numeral 2. So this Roman numeral represents the actual charge of that cation, which has multiple charges. There's 2 different charges for iron. Likewise, this Roman numeral 3 is going to represent the 3 plus charge on this iron. So that's why this is called iron 3 chloride. So example 2 says, hey, go back to example 1 and name each ionic compound. The naming rule for an ionic compound is to name just the cation with Roman numerals if they have multiple charges, and then just name the anion with an "-ide" ending. So the anion takes on the "-ide" ending. And I'll do an example, like a side example. The side example is NaCl. Very common ionic compound to show. So we name the first element, it's called sodium, and then we name the second element with an "-ide" ending. So this is called sodium chloride. So there's your anion with the "-ide" ending. So go ahead and go back to example 1 and name all these ionic compounds. Let's go to example 3. It says to write the formula for the following ionic compounds. Let's go to A. Potassium peroxide. In example 3, we are writing the chemical formula for the following compounds. So we're writing formulas from the name. Given the name, writing the formula. And when we do this, what you should know at this point is your polyatomic ions and what their formula and charge would be. So let's go ahead and look at the first one together. I have potassium, K plus, and peroxide, O2, 2 minus. Now I remember exactly that peroxide is O2, 2 minus, and that's only by pure memory. So you've got +1 and you've got minus 2. So to neutralize that compound, you need to double up the potassium, so you form K2O2. Let's go to B. You've got cobalt 3 plus, and you've got carbonate, which I memorize as CO3 2 minus. And the common multiple out of 3 and 2 is 6, so I'm going to have to double up the cobalt, and then for the carbonate ion, I'm going to have to triple that up. And so because it's a polyatomic ion, I have to I put parentheses to show that I'm tripling the whole polyatomic ion. If I don't have these parentheses, it would look like there's 33 oxygens, which isn't the case. So this grouping right here, the parentheses, will help group the polyatomic ion together. Let's go to C. Now you have cobalt 2 in C. Cobalt 2 is CO2 plus, Roman numeral 2, because that Roman numeral is in fact the 2 plus charge here. And then carbonate, CO3 2 minus. So it looks like one of each of the ions is all I need in order to neutralize this ionic compound. That's precisely what I'm going to do. Going into D, ammonium, memorized, NH4 with a +1 charge. I don't have to put the 1 there. Usually without the number 1, usually it's assumed it's 1. Sulfate is SO4 2 minus. And notice I memorized all of these polyatomic ions and their formula and charge. Looks like I'm going to have to double up the ammonium. And so I will have ammonium sulfate. Sodium hydroxide, Na with a plus. Hydroxide is OH minus. And so it's just NaOH. Again, you should pause at a point where you're pretty comfortable with doing these on your own. I'm just going to finish this set of problems. Chromium OCr. Let me erase that. Cr with a 6 plus charge, and then chloride, ClO2 minus, so that's chloride. And then it looks like I'm going to need 6 chloride ions to neutralize the charge on the chromium 6 plus. So ClO2, and I need 6 of them. Alright, mercury 1, so it's Hg, this is a polyatomic ion, Hd2 2 plus. And then oxide, which is 2 minus, and so it looks like we're going to neutralize these two pretty easily by just one of each of the ions. And so that's your neutral ionic compound. Now we finish it up. Tin with a 4 plus charge. Phosphate with a PO4 3 minus. Common multiple is 12, so I'm going to need to 3 times the 4 plus charge. And I'm going to need to 4 times the phosphate ion. So PO4 is phosphate, and 4 times that would be parentheses 4 on the bottom. Cadmium is 2 plus charge. Permanganate is MnO4 with a minus charge, okay, -1. So it looks like I'm going to have to double the permanganate. So for 1 cadmium, I'm going to double permanganate. Again, always neutralizing the charges of the ions, and that will give you your electrically neutral compound. Okay, let's hop over to example 4. Which ionic compound, sodium fluoride or magnesium fluoride, has a higher lattice energy? Explain your reasoning. The explanation part, I'll verbally explain it. Now, look at the periodic table and find sodium and find magnesium. You'll notice that sodium has a charge of +1 and magnesium has a charge of +2. And so the difference between the two, because they have fluoride already, both the same, they have fluoride ions, the difference is the charge. So it looks like magnesium fluoride is going to have a higher lattice energy. And why it has a higher, magnesium fluoride has a higher lattice energy than sodium fluoride is because magnesium comes as a 2 plus charge versus sodium, which comes as a +1 charge. And so according to Coulomb's law, a higher charge leads to stronger forces. Let's go ahead and look at B. Circle the compound in each pair that has a higher melting point. Higher melting point means the particles are held together strongly, so they have higher force in some way or another. So you're always thinking of it logically. Higher force is what you're looking for. Provide evidence to support for each. So if you look at your periodic table, find aluminum and oxide, and then find barium and sulfide. You'll notice that aluminum oxide has some very different charges from barium and sulfide. Okay, so let's go ahead and figure out what the charges are, because it's either charge or size. And actually, barium sulfide is pretty big also, so it actually has two. Aluminum is 3 plus, barium is 2 plus. Oxide is -2, sulfide is -2. So the charge for sulfide and oxide is not different. It's the charge of the aluminum. Now, aluminum is also smaller. So if you look at aluminum on the periodic table, when it loses 3 electrons, aluminum is now has N equals 2. Barium is N equals, when barium loses 2 electrons, is now on the 5th energy level. So obviously aluminum oxide is going to have a higher melting point not only from the higher charge, but also the smaller size, smaller distance. So charge and distance play a key role in both increasing the force. Now let's go to Roman numeral 2. Strontium sulfide, look at strontium and sulfide on the periodic table. You're always matching the periodic tables. And then calcium oxide. Oh yeah, calcium oxide is definitely smaller. They both they both have the same charges. So if you work out the charges, it's +2, and then -2, -2. So the charges are no different. It's the size. And calcium oxide is has smaller distance ions. So they're smaller ions basically. And then that will increase the force as a result, according to Coulomb's law. C, explain how the melting point of lithium nitride is 813 degrees Celsius, while calcium oxide is 2000 at 573. So must be that calcium oxide is somehow how the force is stronger between the ions. And why that's the case is always, again, exploring the charges. And it looks like to explain this one, you have to, I know you're looking at it and saying, what about nitride? Nitride is a bigger charge for the negative. However, the cation is a higher charge. So overall, what can explain it is that calcium oxide is in fact a higher charge. So higher charge leads to higher force of attraction. Rank the following in terms of melting points. So look at the periodic table and just walk through it and make sure you see where they're located. I'm looking, and I'm going to first do charges. So this is +1, -1, +1, -1, +2, -2. Let me put the charges down here. +2, -2, and then this is +1, -1. So I'm going to do all the pluses in one. They're going to have the lower melting point. The higher ones will have the plus. They're the +2s and -2. Okay. So obviously, the bigger the ions, the lower the melting point. So I'm going to look for lower charge, bigger ions, and that's KBr. And then comes NaCl. And then comes LiF. Notice I handled all of the -1s and +1 charges. So the lower charges are down here. So low charge. Now we go to the high charge. Now, the high charge, the smaller the ions will be higher melting point. So between magnesium oxide and barium sulfide, magnesium oxide is definitely smaller. And so the ions are going to be held tightly together versus barium sulfide. Okay, so this is how I think through the logic. I walk myself through the charges, and then I look at the sizing afterwards. Okay, so this is where my higher charges. So let's talk about crystal lattice, some properties of ionic compounds, and one of which is the crystallic structure. And the word lattice, if you think of like a pie, a lattice pie usually has an interlacing between like a top and a bottom layer, There's a lattice, there's a repeating pattern basically. And this is exactly what you see here, a repeating pattern of one ion versus another versus the same one, and then it's repeating over and over again in this three-dimensional structure. These are all ions, cations and anions, and those ions attract each other very strongly together through electrostatic forces, and this is what makes an ionic compound a solid. So this crystallic structure shows for why an ionic compound is a solid at room temperature. Ionic compounds also are great conductors when they're in solution, when their ions are freed up. And so when an ionic compound goes into solution, this is what you will see happening. You will see, so I drop this ionic compound in water. So the positive ion versus the negative ion is going to be surrounded by water. And the thing about water is, you'll learn this when we get to covalent compounds, but water is a polar covalent compound. And water has these really interesting dipoles where it's partially negative on the oxygen, partially positive on the hydrogens. This is a partial symbol. This delta symbol is a partial symbol. Now, because of these charges on water surrounding the positive ion, this positive ion is going to be the negative end of water. So what happens is water comes in, and I'm going to make water blue, and water is going to encapsulate and surround the positive charge ion, just like this. And then, of course, around the negative ion is where the hydrogens will point and orient themselves around the anion. So that you're seeing what is called opposite attraction. So I'm going to draw some dotted lines to show something called Ion-Dipole Forces. This is Ion-Dipole Forces working out It's an intermolecular force, not an intra. So this is called Ion-Dipole Forces. An abbreviation I like to use in our class is IDF, Ion-Dipole Forces. And the fact that these ions, when they dissolve in water, you'll see an animation in class on this. When they dissolve in water and break up into these water, breaking up each of these ions and cleaving each of these ions away to dissolve that ionic compound, what happens is now you've got ions that are freed up. These cations and anions aren't stuck in this rigid structure. So these freed up ions are now going to conduct electricity. Now we go to another property, brittle. Brittle brittle means it's breakable, pretty easily broken. So it's breakable. Now, let's look at this drawing to help us, this diagram, this modeling. If I have an ionic compound in the lattice structure that you see up here, and I'm just going to do 2 layers, okay? Now, the minute I move and shift this one plane of ions over, so I'm going to shift one plane over, what happens is the positive, negative, positive, and then negative are now aligned to each other. And we know that this alignment is going to cause this substance to break off. So they're repelling each other. You see this positive and positive, repulsion, negative and negative, repulsion, positive and positive, repulsion. So you're going to see this whole layer essentially break off. And I'm going to redraw this broken layer again like this. So they're repelling each other. And this repulsion is because like charges are going to repel. And that's why ionic compounds are brittle. We describe the characteristic as being brittle because the like charges cause the ionic compounds to break apart. And all you have to move over is an ion over. Once you move an ion over, the repulsion occurs between the planes. Let's jump into metallic bonding. Metallic bonding is actually one of the easier types of bonds. You won't see too much going on. Metallic bonding is delocalizing electrons in a sea of electrons surrounding the metal cation. So here are metal cations. I'd like to draw in the electrons. And these electrons are moving about. They're delocalized from each of the magnesium. And they're moving all around. And for every one magnesium, there's 2 electrons. Remember, magnesium has 2 valence electrons. So they're moving about. This is how I show for delocalized electrons. The electrons moving with arrows about this whole structure. And the reason why these electrons move so readily about is because magnesium, a metal, has very low Zeph and a lot of energy levels usually. And so that metal tends to have a very weak hold on their valence electrons. And so that's why those electrons can roam about like this. Now, when I send electricity through, so Mrs. No is going to use a lightning bolt to represent electricity. So if I send electricity through, electricity, all it is a flow of electrons. So these are electrons. Can electrons easily flow through also if these electrons are delocalized and can flow very nicely through? Yes, they can. And so that's exactly what you're going to see electrons do, is they're going to flow through metals pretty easily because metals have that vacancy on their outermost energy, their valence shell. They have a vacant valence shell and extra room for electrons to easily flow. Metal ions are surrounded by delocalized electrons. They're not fixed in a specific atom. They conduct electricity and heat pretty well, as we see here. Alloys. Alloys are basically atoms of pure metal solids, and they're organized in a crystal lattice structure. The atoms of metal atoms are not tightly held, and exist as a sea of electrons occupying interstitial space, so between the metal cores. Alloys are mixtures of different metals that sometimes can fit if there's some empty space. Smaller atoms, metal or other smaller atoms can fit inside of the interstitial spacing. This atomic structure accounts for the metal's conductivity and other products. Oftentimes, alloys are created in order to increase the strength of that metal. For instance, steel. Steel is a metal they use for a lot of construction, building, and such. Steel is made up of iron. And what they do with the iron is they add a little bit of carbon atoms between the interstitial space. And when they do that, they actually increase. Iron with carbon is an alloy called steel. And that increases the strength of that metal. Metallic characteristics. Metals tend to be solids with high melting points and boiling points. And we see this nail. A nail is a solid. You see iron with an iron cation, usually a 3+, with its sea of electrons inside here that's bonded. They conduct electricity, heat and electricity. We did talk about this. Remember how we drew in the sea of electrons? So we drew a bunch of electrons. And the fact that these electrons can move about so easily, when we send electricity through, electricity can move about. Electricity is just a flow of electrons. Electrons can easily move about as well. So once again, I'm going to send some electricity through. Trying to draw a lightning bolt. And what a lightning bolt is just electrons flowing. And so you can actually see them flowing, electrons flowing through a metal, or these gaps for a metal. Okay? And thus it's conductive. Metals are also very malleable. So the malleability of metals and conductivity occurs because these delocalized electrons allow ions to slide without repulsion or breaking of the bonds. So with these delocalized electrons, I can easily take a hammer and move these metals about because of the mobile delocalized electrons. So this very idea of these electrons moving about so easily and fluidly allows me to be able to shape this piece of metal. Thus it's called malleability. We use the term malleability, and ductility means you're able to make it into a wire. So you're able to shape wire as well as shape into different forms. Okay. All right, finishing a metallic, we get into this next category called covalent bonding. This is a gigantic section. It's all on covalent bonding, and it's more complex. That's why this is a very big section. When it comes to covalent compounds, we're talking about sharing between nonmetals. The term that we use is molecule, and the word molecule is always referencing covalent compounds. So this is a molecule called hydrogen chloride. The attractive force in the atoms are called intramolecular forces, and it's measured by something called bond energy. The attractive force between molecules is called intermolecular forces. Once again, we see the inter and intramolecular forces in an atom. And I got cut off, so I'm going to write this in, but This here that you see is intermolecular force. This here that you see is intramolecular forces. Metals, because they have this intermolecular force, and that guides all the properties like boiling point, melting point, vapor pressure, viscosity. All these characteristics are guided by these intermolecular forces. That's why they tend to be gases, liquids, or low melting solids at room temperature or at STP. Covalent compounds are oftentimes insoluble in water, and polar compounds are soluble in water. And that's because water is polar. So the idea that water being polar would not mix with something that is nonpolar, like oil. So oil and water are not soluble with one another, whereas water and something that is polar, water and vinegar. And that's what water and vinegar are very soluble with one another because they're both polar substances. What else is polar? Um, Detergents, or sorry, cleaning solutions oftentimes have polar substances inside. So things that are soluble in water are things that can dissolve, substances that can dissolve. Nonmetals are poor conductors of electricity and heat, and that's because they don't have these ions, freed up ions. They're not even ionic, they're only partially, if anything, polar. Um, there are 7 diatomic molecules that you need to really know, and they exist as di. Di means 2. So it's 2 and 2 atoms. And literally, that's exactly what you see here. They're all 2 atoms, okay? And there's 7 of them. The 7 actually are located in a very interesting way that would help us to remember where they're located. You see how there are 7 of them? And notice the number 7 on the periodic table. I wanted to share this with you so you can see how nice and easy it is to remember the 7. Now hydrogen's over here, so be careful. There's only 6 here, but the 7th one is hydrogen. In naming covalent compounds, you have to use these Greek prefixes. You have to know them, you have to be very familiar with them. Many of them you do know, like the word penta means 5, octa means 8. So some of them you do know. Di means 2. Tri means 3. So tetras, 4. So you do know a couple of, or many of these already. These are Greek prefixes. When naming covalent compounds, what you have to do is you name all the elements by their Greek prefixes. However, you never use the word mono for the first element, even if it's 1, if there's 1 atom of that element. So let's look at the first one. Here you have 1 carbon. Never use mono for that first element. So you call this carbon. Now the second element, you can use mono. So this is called carbon with mono oxide. So you still have the "ide" ending, just like you name ionic compounds. But you have these prefixes to add to it. So this is called carbon monoxide. Now sometimes you're going to have to drop, if you see double vowels, you will drop those double vowels, especially if your prefix has a double vowel with the nonmetal or the atom. All right, let's look at the next one. Carbon, you don't use mono for carbon, but then there's two oxygens here, so we call it 2 di, and then you call it oxide. So this is called carbon dioxide. Naming, once again, always, once you feel the flow of things, please make sure you just try it on your own. The next one is nitrogen. I see 3 bromides. So 3 is tri. So tribromide is my answer. Finishing the rest. I see 2 phosphorus and 5 sulfide. So I'm going to call this diphosphorus. Pentasulfide. And then the last one, tricarbon, tetranitride. Okay. Now we go to the writing formulas. There's 2 substances that you have to memorize, and that's ammonia and water. Ammonia is a simple formula. It's just NH3. Water you know as H2O. So those 2 you will never have any problem. Now, oxygen, these are really easy. You'll find writing formulas for covalent compounds to be very easy. So monosulfide, OS. Selenium, Se, difluoride, so it's 2 fluorines. Because it basically tells you how many of each atom. You don't have to neutralize these compounds. Tellurium, dibromide. Diphosphorus pentoxide. Phosphorus trihydride. Once again, you should pause when you find yourself feeling pretty good and just work through the rest. Now this one's a little harder. Remember how I said chlorine? If it's an element, this is actually a covalent diatomic molecule. So you're looking at if it says it's the pure element chlorine, chlorine doesn't like being by itself. It actually likes to bond diatomically. So chlorine is Cl2. All right. Now let's jump into Lewis structures. There's a priority list to how we do this, okay? I'm going to go over it, but I would like to make sure you're always checking. You see this little check? That means you're checking for octets and duets for periods 1 and 2. And then you want to try to minimize formal charge. You don't know what it is yet. You're going to be, I will discuss what formal charge is later on. So the first thing you want to do when you draw a Lewis dot is you always want to start with the central atom. Usually it's the least electronegative, except for hydrogen. In other words, hydrogen is never a central atom, okay? Think symmetry around the central atom when you're doing it, when you're drawing. You draw the Lewis dot for each bonded atom encircling the central atom. Try to draw the bonded atoms near the unpaired electrons of the central atom in preparation for bonding. And then 3 says to single bond, make what is called a sigma bond. It's called single bonds are sigma bonds, only from the central atom to the bonded atoms. And then notice there's a check. That means you're going to check for duets and octets at this point, okay? And then you go for, when it comes to polyatomic ions, you add your electrons for the anions, and then you subtract electrons for the cations. And then you include the formal charge as you're adding electrons or subtracting electrons. And again, once again, you check for octets and duets. Then you go and do your multiple bonds, which are called your pi bonds. And those pi bonds are like your double and triple bonds. Once again, afterwards, you check to make sure you have an octet or duet. Some atoms have an expanded octet. Those atoms actually have empty d orbitals, which means empty means there's room for more bonds. And so those expanded octets occur with the idea that you're making having more than 8 electrons around that atom as a result of sharing with other atoms. And the 2 atoms that we will focus on are phosphorus and sulfur. Now, how do I know how much phosphorus and sulfur can expand its octet? Well, count how many valence electron phosphorus has. Phosphorus has 5. So when you share, each time you share, you're sharing with one other electron of the adjacent atom. So 5 times 2, if you're sharing each one of these valence electrons with that atom, or with 5 other atoms, that will give you 10. So a way for us to know is to count your valence electrons and times it by 2. And that is how much you can expand your octet. So phosphorus can have 10 electrons total around that atom, including the shared ones. Same here with sulfur. Sulfur has 6 valence electrons. Times that by 2 gives you 12. So sulfur can have 12 electrons, including the shared electrons. And so it can have an expanded octet. That is called your greater than 8 electrons. There's also incomplete octets. Usually for incomplete octets occur with less than 8 electrons for smaller atoms, specifically boron and beryllium. So we're going to do the same kind of mathematics. Boron has 3 valence electrons. Times that by 2 gives you 6. Notice 6 electrons is what beryllium can bond, sharing with 3 other atoms. And so that is an incomplete octet. Beryllium has 2 valence electrons. Times it by 2 for each bond that it can make. And that will be 4 electrons total. And that, once again, is an incomplete octet. Notice less than 8. Notice greater than 8. So you have expanded octets or incomplete octets, like these 2 atoms. And usually these are the only 2 examples of an incomplete octet. There is an exception. Nitrogen goes through some really funky reactions in what is called an odd number of electrons, but we don't cover it in honors chem. Even AP doesn't cover it. So once you get the reason why we don't cover this is because nitrogen, actually, that reaction occurs in the higher atmosphere, not on like our troposphere. Okay, so it actually doesn't occur around our environment. It actually occurs up in higher atmosphere. All right, let's go to example 7. Draw the most stable Lewis structure for each. Count the number of pi, sigma and pi bonds for each structure. I'll help you with that once we do this example, what pi's and what sigmas are, okay? The first one is water. So I follow these rules. I'm always going through step by step in this priority order. I start off with the electron dot of the central atom. Who's my central atom? It's the least electronegative, other than hydrogen, so it can't be hydrogen. In this case, it's going to have to be oxygen. I draw the number of dots for the oxygen. And it looks like, I'm going to draw this dot up here. Okay, it looks like I have 2 spots for bonding. Right here, unpaired, and right here. So I'm going to prep up my 2 hydrogens. My 2 hydrogens are going to be prepped up over here and down here. And that's because I can easily bond them. So here's my hydrogen. And I like putting the electrons over on the side where I can bond them, or on top where I can bond. So I'm always making those unpaired electrons available for bonding. And then now I'm going to do a sigma bond. So each bond is 2 electrons, so a pair of electrons, okay? Now I'm following my steps very clearly. Notice I did all my bonded atoms encircling my central atom. I drew the dots for them. And then I did my first sigma bond. And that sigma bond is this bond right here. It's the true bond that occurs between the atoms. So here's one sigma bond, and here's another sigma bond. So there is a total of 2 sigma bonds. This is a sigma symbol. There is 0 pi bonds. Let's go ahead and look at sulfite ion. Drawing sulfur as the central atom, the lesser electronegative atom will be the central atom. I'm going to represent the dots for sulfur. Okay. Now I notice two unpaired electrons, and so I'm a little tight for space. Okay. And then once again, 6 valence electrons for oxygen. So I'm going to draw the 6 in. A little tight for space, but it's okay. Okay. So now I'm ready to do connections. Here's my sigma bond. I know these two are unpaired, so I'm going to bond those two. These two are unpaired, also I'm going to bond those two. Now I have to bond this oxygen to the sulfur, so I'm going to have to break up this paired electron and just bond it. I don't care. I'm just going to bond it, okay? I have to bond them. So here's my next sigma bond. Okay. Now, I need to add, according to my rules, I'm following my rules. I know you're going, but Mrs. No, you're not telling me I'm following the rules, but I'm following them. And I'm always looking out for the rules to make sure. You've got to get used to these rules, and that's what I've gotten used to know what I'm doing next. The next thing I'm doing is 4, which is for polyatomic ions, you have to add electrons where you need to or subtract electrons. If my ion is an anion, like this, it's an anion, I know that I am going to add 2 electrons. That's what that -2 means. So I'm going to have to find a place where I can add 2 electrons. And the best place is where oxygen is, because oxygen needs those electrons more than ever. And so I'm going to put it right here, and I'm going to put a -1 because I added an electron on that oxygen. I'm also going to add an oxygen over here, and so this is also going to be a -1. So notice how the charge of this whole substance is -2 overall, and that's what sulfate is usually. But I haven't quite checked my octets, so I'm going to count my octets really quick. Do a quick check of octets. 2, 4, 6, 8. This looks good. This oxygen looks good. 2, 4, 6, 8. This oxygen looks good. 2, 4, 6, 7. This oxygen does not look good. Let's go around the sulfur. 2, 4, 6, 8, 9. Yikes. This oxygen or sulfur can have an expanded octet. Don't recall that it can actually go up to 12 electrons. And so in order for this to happen, we're going to do what is called a multiple bond. It's called a pi bond. So I'm going to connect these two guys together, and that will give oxygen 2, 4, 6, 8. So there's an octet there. Sulfur now has 2, 4, 6, 8, 10. So sulfur actually can have maximum 12 electrons. So 10 is quite alright for this substance. So this is the best Lewis structure that I can represent for sulfite ion. Sigma bonds. Let's count the sigma bonds. They're the true bonds that occur initially between the atoms. So here's 1 sigma bond, 2 sigma bond, 3 sigma bond. Okay. Now the second bond is called a pi bond, and notice that there's only 1 pi bond. So I have a total of 3 sigma bonds and 1 pi. Pause if you're able to pause to work through these problems on your own, but I am going to continue on working through them just to make sure you're watching me be able to draw the structures. Okay, so my next one is nitric acid. Now nitric acid has nitrogen in the center with 5 valence electrons, and then I'm going to position the 3 oxygens around, and I know that this hydrogen right here is going to be on one of the oxygens. Okay, so I just know that it's an acid, and acids are going to just attach, the hydrogen is going to attach on the oxygen. Oops. Okay, now 6 valence electrons I do my sigma bond, sigma bond, sigma bond, and here's my sigma bond. So I've got all my sigma bonds in place. Now I count. I'm always checking my octets really quickly. 2, 4, 6, 7, not good. 2, 4, 6, 7, also not good. 2, 4, 6, 8, good for this oxygen. Duet, great for hydrogen. Let's count nitrogen. 2, 4, 6, 8. So nitrogen does have 8, but these two oxygens do not have the 8 that they need. Now you're going, Mrs. No, why don't you just bond these two guys here? That will give them both 8. But you never see a cyclic triangular structure like this. Never ever a cyclic triangular structure. So this is not, this bond will not happen. So what we're going to have to do is play with this paired lone pair up here on the nitrogen. We're going to separate it basically. So separating it, I'm going to take this right here and bond right here. But I'm going to move it down, okay? So I'm going to move this electron down right here so I can bond. That means I'm going to erase this. Oops. Erased a little bit too much there. Okay. So I erased, and I'm putting that electron down here where I'm going to do what is called a double bond. And so then, again, I'm always assessing what's happening. I'm counting my electrons and seeing how many I have. 2, 4, 6, 8. It looks like it's good for this oxygen. We've already worked out this oxygen and hydrogen already, so it's good. Let's count nitrogen. 2, 4, 6, 8, 9. So 9 here. 2, 4, 6, 7. 7 here. 9 and 7. 9 and 7. How do we get each one 8? Well, I would need to pull the one that has 9 and bring it over to the 7. So literally, I can actually move structures, move electrons around in an atom. That will actually cause formal charges, of course. So in removing an electron on that nitrogen there, I have a formal charge of +1. In gaining an electron here, I have a formal charge of -1. We will learn how to calculate formal charge soon enough, okay? We're actually going to learn how to do that in a formal lesson. For now, you just see that whenever you're transferring electrons, you're going to make sure you put charges where the electrons are gained and where the electrons are lost. Okay, so now I go to the next. In the next, I've got carbon as my central atom, 4 dots, 4 valence electrons. Nitrogen, 5 dots. Hydrogen, 1 dot. I do my first sigma bond. I look to see if I need to add electrons. It looks like I do not need to add electrons to the structure. Remember, this one I didn't need to add electrons either. I only transferred the electrons between the atoms. I now need to see if I have an octet. 2, 4, 6. I only have 6 around this carbon. 2, 4, 6 around this nitrogen. So it looks like I'm going to need to do some more bonds, some more bonding between the atoms. Here's another bond. And that will increase the number of electrons. So you count it and you can see 2, 4, 6, 7 now. Earlier there was only 6, now 7. So adding multiple bonds increases the amount of electrons that atom has because it's now sharing with another atom. Likewise, nitrogen has 2, 4, 6, 7 also. So now both of them have 7. Why don't we share another bond between the atoms? Oh, I did forget to count sigma and pi bonds over here. So we'll do it for both C and D right now. I count 1 sigma, 2 sigmas, 3, and 4. There are 4 sigmas. And then there's also a pi bond right here. So there are 4 sigmas and 1 pi. Okay. Now we go over to this substance here. I see one sigma. The true bond that's between the two atoms is my sigma. Here's another sigma, so there's two sigmas. That means I have two pi's. These are two pi bonds. So a triple bond actually has one sigma and two pi's. A double bond has one sigma and one pi. So my tally is I've got two sigmas and then I have two pi bonds. All right, let's look at the next. Now, in the next one, you'll notice two carbons, which means I'm probably going to have two central atoms here with hydrogen surrounding as bonded atoms. So I'm going to draw both carbons, two central atoms. Sometimes you can have actually multiple central atoms. 4 valence electrons. And then symmetry is really important. So the 4 hydrogens that I see in this formula, I'm going to divide 2 on this side and then another 2 on this side. So I'm going to put hydrogens, one here, and I'm going to put one on the bottom. I just chose to put it on the bottom. And the same here, one on the bottom and then one over here, okay, on the right hand side. So let's go ahead and do my sigma bond. Sigma, 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 sigma. And then I realize that I know you can catch this pretty quickly. I realize that there's not an octet here, and there's one here, one here that's still unpaired. Why don't we just bond it as a multiple bond? In other words, a pi bond. And that's exactly what I'll do. You get really good at seeing things eventually. So sigma and pi's, I see 1, 2, 3, 4, 5. 5 sigmas. And I see 1 pi. Let's do carbon dioxide now. Again, 4 dots for carbon. Oxygens, oxygens. I'm going to put my unpaired down here. I'm going to alternate. That's what you're seeing. I'm unpaired up here, unpaired down here. Because remember, I'm just trying to think the possibility of bonding always. So now sigma, sigma. I look and count to see if I have an octet, and it looks like I'm deficient on all the atoms. So I'm going to do another bond here, and then also another bond here. And then I check to see if I have my octet, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So it looks like it's all octets. Let's count my sigma and pi bonds. I have 2 sigmas, and I have 2 pi's. All right, let's talk about resonance. Okay, so experimental evidence shows that in a compound like ozone, the bonds are identical. To represent resonance, we show all the possible loose structures with a double arrow in between. Make sure to move only the double bond, not the element. Resonant only often applies when you have a double or triple bond where the pi electrons are delocalized around the entire molecule. So the word delocalization, just like in metallic bonding, is the same idea for pi electrons, where they're delocalized in the entire structure. A molecule distributing equivalent bonds called bond order or effective number bonds. We're going to actually learn how to calculate the bond order and understand what the bond order is. So something like ozone. Here I've drawn ozone. And notice how this pi bond, this double bond right here has a pi electron. I can move it over to the other side. When I move it over to the other side, notice the electrons, the double bonds on the left side now. Now, notice the pi electrons moved over, so we call that delocalizing. Both the oxygen-oxygen bonds of both resonance structures allow us to be able to say that this bond right here is equivalent to this bond. So if I try to break this bond, it's actually equivalent to this bond. And how that's possible is because of resonance, where the pi electrons can move over to the other side. So we can equate these bonds, these oxygen-oxygen bonds. How do we equate it? Well, they have one sigma bond. Both of them have one sigma bond. But the pi electron is moving over and shifting back and forth between these two sides here, which means that pi electron is shared between the two, which means it's a bond and a half, 1.5. So the bond order is 1.5. Now you're going, how do I see that? Well, a good mathematical way to do it is to say, okay, there are 3 total bonds, 2 sigmas and 1 pi. So that's total 3 bonds. 2 atoms bonded to the central atom. Notice when you take 3 divided by 2, you get 1.5. So each of these bonds right here is technically not a double bond. It's actually a bond and a half. And that bond and a half between the two sides is what really, if you take a bond and a half plus a bond and a half, you get 3 bonds total. So resonance allows us to say, hey, in ozone, when we break these bonds, they're equivalent bonds. And they're equivalent bonds because of the idea that pi electrons can travel back and forth, creating the same bond order or the same number of bonds. What you're going to do is you're going to draw the resonance structures for these 3 substances, and you're also going to calculate the effective number of bonds. So let's take a look. This is a negative symbol, by the way. It's kind of hard to read, but it's nitrite ion. This is also negative. It's carbonate ion. This is also negative. So if you want, you can draw that in a little bit clearly so you can see it. Sorry, when it gets converted, it makes a very smaller charge there. This is -2, by the way, so make sure you remember nitrate ion or carbonate is a -2 charge. All right, let's go ahead and start with, I'm going to draw the first nitrate ion, and I'm really going to have to squeeze because I don't have much room. So nitrate ion is nitrogen, or sorry, nitrite ion is nitrogen in the center, 2 oxygen. So 1 oxygen right here, and I'm going to put it on the opposite side, oxygen. Now you're going to see me take some shortcuts. And one of the shortcuts that I'm going to do is, if I know that oxygen is going to take on a lone pair, is going to be like paired and not bonding in any special way, I'm going to just draw lines to represent that pair of electron. So each of these lines is a paired of electron. So here I'm introducing a nice shortcut for you. Alright, so I'm going to do my sigma bond. Oops, there's a crooked sigma bond. That's okay. Now I know that I'm going to add 1 electron, as I see right here. So this is the step that I actually add 1 electron to the structure. And I'm going to add it to the oxygen. Why? Because the oxygen not only is more electronegative, but the oxygen needs it more than the nitrogen, okay? Now, I see another multiple bond that can occur here, but it's crooked. So I'm going to move this paired electron down here. So sometimes you're going to have to move structures around. So I'm going to move that paired electron down here. Oops, I didn't mean to make it that color, but it is. It's okay. So the pair goes down there, and then I'm going to erase there. So I'm going to erase that. And then now I can actually do my bond, okay, without making it look awkward. So there's a double bond between nitrogen, oxygen over in this side. Notice the charge overall is -1, and there's a -1 charge on this oxygen. So check my octets and duets. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Ooh, this structure looks fantastic. It has an octet like we would like and hope for it to have. Okay. So I do like to put brackets around to show for charge. So I'm going to put a bracket around this nitrate ion, and then I'm going to put a -1 charge because that's the overall charge of that whole ion. Now you're going, is there a possibility for, first of all, is there a pi electron? If there's a pi electron and there's a possibility for me to move over to re-represent this structure and still make and it still is nitrite ion and it still follows all the octet rules, then you have resonance. And so my resonance structure, once I have my first structure, is easy to do. What I do is I just look and match. I put my double bond on this side, and on my double bond is two lines, two lone pairs basically. So I'm going to put two lone pairs. On the other side, this is a cleaner structure by the way, is an oxygen, and I know that there are three lone pairs around that. I know you don't know what lone pairs are, but and then the charge is a -1 charge here, and of course overall the charge is -1 overall. So this is the resonance structure. Now it says to calculate the effective number of bonds. Once again, my math comes into play. There are 3 total bonds divided by the 2 atoms that are bonded to this. So in other words, there's 1 sigma plus this pi that gets shared between the 2, split between the 2, which means I have an effective number, or the effective number of bonds is 1.5. 1.5 for each of these, of course, okay? So please be aware it's each 1.5. That's why when you add 1.5 plus 1.5 gives you 3. Let's look at the next structure. We're going to need a lot of room, so I'm going to make this small. Oxygen, oxygen, and oxygen. So again, if I know I can take some shortcuts, I'm going to take some shortcuts. I do my sigma bonds. I always start off with my central atom in sigma bonds, and then I know to add 2 electrons because there's a 2 negative charge here, and that means I need to add 2 electrons to the structure, and this is when I'm supposed to add my 2 electrons after my sigma bonds. So let's see, let's add an electron on this oxygen. And I'm kind of anticipating a double bond or a pi electron right here. So I'm anticipating that. So that's why I'm not really going to write or add the electron there on that oxygen. I'm just going to add it on this oxygen on the bottom here. Now notice the -2 charge, and then I'm going to check my octets. So I check 2, 4, 6, 7, not good. 2, 4, 6, 7, also not good. So these two are 7, and they also have an unpaired electron. I can tell that I'm probably going to do a double bond right here. So I'm actually going to put that double bond in because I can see that. And I hope you can see it. I'm going to put brackets around and put a -2 charge overall. It is getting kind of messy here, but we're going to squeeze in, okay? So carbon, I'm going to move the double bond on the bottom oxygen, and then I am going to -1, -1, so this is the -2 charge. So here's another resonance, and all I've done is I've taken the double bond and moved it down to this oxygen right here. So there's one more resonance structure. Once again, I'll really squeeze in on here. Once you have your initial Lewis structure and it's a solid Lewis structure, you can then draw the other resonance pretty easily. And you know the shortcut, so it's kind of nice. there is our third resonance structure. Okay, so let's calculate the effective number of bonds. Once again, they all have a sigma bond, but then now this pi bond is split among 3 of these atoms, so it looks like a third. So 1.33 is the bond order. If you'd like to do the math, 4 divided by 3 gives you 1.33. Okay. All right, the last structure, hopefully you can pause if you feel pretty comfortable and confident about doing that. Go ahead and do that. Once again, I'm going to do carbon in the center, oxygens, 2 oxygens, and then the hydrogen. Hydrogen is going to be in this structure. I do my sigma bonds. And then I add my electron. And it looks like I'm going to have to add 1 electron according to this. So add 1 E minus. And so I know to add it to my bonded atoms. My oxygen is the ideal spot, this one. Why didn't I do it on the top oxygen? Because I'm anticipating another bond. So I actually am going to bond it because I know that they both lack an octet of electrons. All right, so in this structure, once again, I like to show my overall charge. It's -1. And so there's another structure for this. It's carbon. Put the double bond on the bottom. And my negative charge is on this oxygen. And my overall charge is a -1. Now, calculating the effective number of bonds. Now, I cannot move this the pi electrons over to the hydrogen, okay? Because hydrogen can only make one, it only has 1 valence electrons, and it has already fulfilled the duet rule. So you cannot move the pi electrons over to here because it actually will create a completely different structure. You're trying to re-represent the same structure, okay? So what is the effective number of bonds? I'm going to do all the bond orders. This one's 1 bond order, and we use the degrees symbol for the bond order. This is 1.5 bond order, and as is this between the carbon and oxygen. So those are your bond orders. We're going to now cover formal charge. And so, what is formal charge? It's literally the charge on atoms in a Lewis structure. So, to calculate formal charge, you take the difference between the valence electrons in an isolated atom and the number of electrons assigned to that atom in the Lewis structure. The best Lewis model can be determined among several possible resonances as the one with the least formal charges and has an octet is going to be the best Lewis structure. So we're going to do that. We're actually going to draw at least 2 possible Lewis structures assigning formal charge, and then we're going to justify which one's better. So let's start with the first one. The first one is formaldehyde, and it has carbon as our central atom. Carbon oftentimes is a central atom. Oxygen. I'm going to take my little shortcut for oxygen. And then there's hydrogen. And then there's another hydrogen. So you're going, why did you put the hydrogen on top and on the side? Because I'm anticipating the possibility of a multiple bond here. And so that's why I've decided to put the hydrogens where I situated them. So I'm going to do my sigma bond. Okay, so those are all my sigma bonds. And then I check to see if I have an octet and duets. So duet for hydrogen, duet for hydrogen. There's 7 electrons around this carbon, and then there's also 7 around this oxygen. So it looks like 7 and 7 between the two. We could probably do another multiple bond. In doing another multiple bond, now let's go ahead and calculate the formal charge. By the way, I'm going to do another Lewis structure later, and we're going to calculate formal charges for each of the atoms in that structure. But let's do this first structure. We know it looks pretty good. You have octets for your atoms. I'm now going to calculate formal charge. So to calculate formal charge is to do the valence electrons of hydrogen. So following this equation, I'm going to first start off with the valence electrons of that element, and hydrogen has 1 valence electron. And then I'm going to figure out how many electrons are assigned to that atom. So I look in the structure and I see only one of them actually belongs to that atom, and that's the one that is assigned to that atom. So the number of assigned electrons is 1. So what's 1 minus 1? That equals to 0. So the formal charge on that hydrogen is 0. I do the same thing for this hydrogen on the left. So 1 minus, there's only 1 electron assigned to that hydrogen that belongs to that hydrogen. So 1 minus 1 is 0. Now we go to carbon, the formal charge of carbon. Carbon has 4 valence electrons minus number of electrons assigned to that carbon is 1, 2, 3, and 4. So 4 minus 4 is going to give you 0. So the formal charge there is 0. I like to put my zeros with a slash through it just to make sure you see it as a 0. Now we go to oxygen, 6 valence electrons. How many electrons assigned to that oxygen? 2, 4, 5, 6. So 6 minus 6 has a formal charge of 0. So all of these atoms in this structure has 0 formal charge. Now let's look at the second structure. So when I draw the second structure, I'm going to redraw a different possible structure. So again, I start off with all my atoms, and I position my electrons or my atoms where I originally had them in the previous structure. But now I'm going to do my sigma bond. Okay. So far it looks the same as the previous structure. However, right now what I'm going to do is I'm going to try to recreate a different structure. And how I'm going to do that is, see this electron right here underneath the carbon? I'm going to move it over here. Upon moving it over here, now you have a form, something's going to happen with that carbon as well as oxygen. So I'm going to erase this electron and move it over to the oxygen. And it does make sense that this is a possibility because oxygen is more electronegative. So it makes sense that oxygen will have the shared electrons moved over to its nuclei or nucleus, spending more time around the oxygen's nucleus than the carbon. Now, let's go ahead and calculate formal charge. 2 minus 2. Oh, I'm so sorry. 1 minus 1. So 1 valence electrons, only 1 electron assigned to that atom, so its formal charge is 0. Hydrogen, 1 valence electron minus 1 assigned to that atom, the hydrogen, with a formal charge of 0. Carbon, so let's look at carbon. Carbon has 4 valence electrons, and I actually only see 3 electrons assigned to that carbon. And so that's why I'm going to write 3 as the electrons assigned to that carbon, giving carbon a formal charge of 1, plus 1. Oxygen, 6 valence electrons minus, and it looks like there's 7 assigned to that oxygen. And let's count that together to make sure we see the 7. 2, 4, 6, and 7. So this all belongs to the oxygen. And so when you subtract those numbers, you get a -1. And that actually makes sense because didn't that one electron that was on carbon transfer over to the oxygen? So oxygen gained an electron, -1. Carbon lost an electron, so carbon has a +1 formal charge. So the question is, between these two structures, which one is better? And the one that's better is the one I'm going to circle, okay? And that is the one with the minimal formal charge, as we stated up here, the least formal charges, and has an octet. This carbon doesn't have an octet, and it has a formal charge. This oxygen does have an octet and also has a formal charge. These do not have any formal charges, so the starred one is the best one. And that's because you're trying to minimize the formal charge. I'll put a star next to the better structure. All right, let's go on to the next one. In the next one, carbon is the central atom. By now, you should be pretty good at memorizing, honestly, all the valence electrons for most of your elements. Okay, now I do my sigma bond. Okay, now this negative means I'm going to add an electron, one electron to the structure, and usually I'm going to add it to the one that is more electronegative, oxygen. And so there's a -1. And I actually will see the formal charge to be -1 later. And so now I'm looking at the structure and seeing where I have an octet. I'm always counting my octets. 2, 4, 6, 8. This checks. This is a good atom with an octet. 2, 4, 5, 6, not enough. 2, 4, 5, 6, also not enough. So when there's not enough on two atoms, oftentimes that suggests that there is going to be multiple bonds. And that's exactly the triple bond, the pi electrons that I'm going to connect between the two. So let's go ahead and figure out the formal charge. Calculating formal charge in blue, so you can see that. 6 minus how many electrons assigned to that atom? There's 1, 2, 3, 4, 5, 6, 7. There is 7. So 7 it is, minus 1. And that matches up with the -1 that we see down here. So here's -1 and -1. Same charge, formal charge. Should be expected to be the same. So 4 minus 4, formal charge of 0. And then for the nitrogen, 5 minus 5, formal charge of 0. So in this structure, you do have a formal charge, but note that the formal charge is the fact that this ion, this polyatomic ion, has a charge in itself, whereas this structure didn't have. An A formaldehyde did not have a charge. So that charge is necessary, and so you're expecting to see a permanent formal charge on one of these atoms. So let's look at another possibility in terms of structure. In this next structure, you're looking at carbon once again. Oxygen. And in this next structure, I'm going to move electrons around if I need to, okay? So it looks like I'm first going to add an electron to an atom. Let me just decide, I'm going to change it up and add it to this nitrogen. And that will give me a -1 formal charge from that addition, okay? Now, we know that's not going to happen, but then, oh, sorry. Now then I'm going to check to see if I have an octet. I'm always going to show the right approach, okay? So 2, 4, 6, 2, 4, 6, 7, 2, 4, 6, 7. So it looks like I have 7 here and 7 here and 6 on the carbon. So it looks like I don't have a complete octet yet. It looks like I'm going to have multiple bonds. And so here is my multiple bond. Double bond here and a double bond here. Let's look at the formal charges, okay? calculating formal charge. 6 minus 2, 4, 5, 6. So 6 assigned to that atom, so it's 0 there. Carbon, it's 4 minus, there's 4 assigned to that atom, so it's 0 also. Nitrogen. Nitrogen has 5 valence electrons. Let's count this one closely, okay? So we have 1, 2, 3, 4, 5, 6. So there's 6 assigned to that atom in this structure. So the formal charge is -1. Okay. So far we've got this other structure. Now we go to the third possibility. In this third possibility, I'm probably going to take the pi electrons and move it over here and make a triple bond on the carbon oxygen. Not to say it's going to happen, however, we're really exploring all the possibilities, okay? Once again, drawing these. This time I'm not actually going to draw lines around the oxygen because I'm probably going to have to do. So now if I triple bond this, I'm going to do this and this. That means I'm probably going to, one of the electron is probably going to have to move over to the nitrogen, okay? So I'm going to have to move this one over here. And that means I'm going to erase this electron. And also the movement. I'm going to erase that movement to not clutter. And so I'm going to move an electron over here. Oops, I'll make it in black so you can see the addition of an electron. That will then also, we're going to gain an electron. So that is -2 overall. And now we're going to calculate the formal charge. So 6 minus 2, 4, 5. So this is going to be a 5, and that equals +1. For the oxygen, or for the carbon, 4 minus 4 is equal to 0. And then for the nitrogen, 5 minus 1, 2, 3, 4, 5, 6, 7. So there's 7. So the formal charge is in fact -2, as we see right here as well. So the -2 actually matches to how many electrons were added to this nitrogen atom. So out of the 3 structures, which one is best? Well, I know that this structure has only formal charge around the most logical atom, which is the oxygen, which is more electronegative. This structure, we have a formal charge on the nitrogen, which isn't as logical as over here because the nitrogen is not as electronegative as the oxygen. Remember, oxygen has a greater Zeph value. Over here, there's way too much charge. There's a charge on the oxygen here, +1. And then there's a charge of -2 on the nitrogen. So this structure is actually the worst of the 3 structures. So which one's the best? We found out that the one that offers the logical number of electrons, or the added electron on the oxygen, which is more electronegative. All right, let's look at the next one. In the next one, you've got carbon. You've got hydrogen, and then you also have oxygen. I'm going to take my shortcut, and then my nitrogen, and then I'm also going to have 2 hydrogens on the nitrogen, as the structure suggests. 2 hydrogens on the nitrogen right here. That's why they're attached together. I draw my sigma bonds. And then I count my octets and see that both the carbon here and the oxygen here do not have a complete octet. They both have 7 here and then 7 here. So the best thing to do is do a multiple bond between the atoms. When there's deficiency between two atoms, it means you're going to share another bond, and it's usually a pi bond. So here's a structure. And in this structure, it looks like everything checks out. Formal charge wise, now I'm going to do it in my head also. So I'm going to calculate it and go, okay, here I have 6 valence electrons, and then I have 6 assigned to that, so it's 0 here. Hydrogen, 1 valence electron, 1 assigned to it, 0 here. 4 valence electron, 4 assigned to that atom, so 0 here. 5 valence electrons and 5 assigned to that atom, 0 here. So they all have 0 in the end as I look and get really keen on seeing formal charge. So they all have 0. This is a good structure if you've got the least amount of formal charge. So it might be the best structure. Let's now look at the other possibilities. In the other possibilities, I'm going to move the pi electrons over to the nitrogen right here. And as a result, I'm going to see a different structure from that, with formal charge probably. And notice I'm very patient with drawing my structures, making sure I see what I'm supposed to see through this. Okay. So in this structure, I'm going to break free and do another bond right here. And then I'm going to move this electron over. I'm going to move this electron right here over to the, I'm going to allow am I missing a hydrogen? I am actually missing a hydrogen, sorry. No wonder I'm looking at it and going, there's something missing here. There's a hydrogen missing. So I'm going to move this electron over to the oxygen over here. So I'm going to erase this. And then I'm going to move it over to the oxygen. And that should give me a +1, and then this should give me a -1. Calculating formal charge, I'll see that this one has a -1 formal charge. This carbon has a 0 formal charge. Hydrogens both have 0 formal charge. Nitrogen here has a +1 formal charge. Hydrogen is 0. So unlike this structure up here, the first one we drew, there's 0 formal charge all across. Here you have formal charges within the atoms. And so, again, minimizing formal charge. All atoms have an octet in this structure, so it's actually pretty good in terms of octet. However, we're trying to minimize formal charge. So, we can draw another one. There's another structure. I'm going to go fast on this one. The second structure is going to be one where we're seeing the electrons all being carried over to the oxygen. So there's electrons carried to the oxygen, carbon, once again, bond here. I am taking a shortcut just for the speed of things here. There's still going to be bond, bond, bond here. And now you're seeing an electron move. Because there's an electron that moved over, so formal charge wise, there is a +1 formal charge on this carbon. Because 4 valence electrons and only 3 are assigned to that atom, that's the +1. This one, 6 valence electrons minus 7 assigned to that, so there's a -1 formal charge. All the other atoms have a 0, 0, 0. Once again, this last structure has a lot of formal charges, so the best structure among all of them would be the first one, where there's no formal charge. So 0, 0, 0, whereas this one has -1 and +1. So the big takeaway is when you're drawing structures, if you have a very small amount of formal charge, if you have minimal molar charges, you will see a structure that's the best. And usually it's the first one you draw, the one that logically sequences through the rules that you have learned for drawing Lewis structures. Covalent compounds, when they bond with multiple atoms and they share electrons with those multiple atoms. Because those electrons are bound between the two atoms that are sharing those electrons, we create these lovely little shapes. They're called geometry, molecular geometry. And these shapes are guided by a theory called the VSEPR theory. The understanding that valence shell electron pairs repel, so this is called the valence shell electron pair repulsion theory. Electron pairs around a central atom that's sharing electrons are going to find a way to orient themselves as far apart from each other as possible due to electron-electron repulsion. We're about to watch a video that describes all these geometric shapes that molecules in nature they assume, and they are created as a result of this VSEPR theory. A good way to help you is to also have some grapes and toothpicks in the house to help build these shapes. I'm going to assign effect animation and simulator for you to work through to study these shapes and practice these shapes. But let's learn about these different shapes through this video.
The electron pairs that surround a central atom are most likely to be found in confined regions of space called electron domains. The arrangements of the electron domains about a central atom are determined by the electrostatic repulsions between like charges. The electron domains stay as far apart from one another as possible, while at the same time they are held by their attraction for the central atom. When there are two electron domains about a central atom, they are located 180 degrees apart to minimize repulsions. Three electron domains about the central atom take up positions in a plane separated by 120 degrees. Four electron domains form a tetrahedral arrangement about the central atom. Five electron domains form a trigonal bipyramidal arrangement. Two of the electron domains are disposed along the vertical axis. The other three are found in the horizontal plane, separated by 120-degree angles. Six electron domains are located along the X, Y, and Z axes at 90 degrees from one another. This arrangement is termed
So this chart is a
octahedral.
graphic organizer of all the 5 different electron geometries that we saw in the video and the derivatives that come off of that electron geometry. Now the derivatives are basically lone pairs in lieu of a bonded atom. So you have a lone pair in lieu of one bonded atom, causing the bond angle to basically squeeze for 2.5 degrees. So normally this is 120 degrees. With that lone pair on top there, this bonded angle ends up being 117.5 degrees. So it's a 2.5 degree squeeze. Likewise, over here, here's a lone pair that's substituted for the bonded atom up on top. So now the bond angle, instead of 109.5 degrees, is now 107 degrees. And each time I add a lone pair, that causes a 2.5 degrees. So 2.5 less from 107 is 104.5 degrees. Now, it really does depend on where you put the lone pairs. If the lone pairs are on an axis that counterbalances, you won't see that lone pair affecting the bonded atoms like you see here. So the 90 that you saw here is still the 90 right here for the bonded atoms. So it really depends on where those lone pairs are repelling and causing the greater repulsion. If they counteract like here, you will not see an effect on the bond angles. So this is a great graphic organizer for you all to just study, and as you get more exposure to practicing these shapes, you'll find yourself feeling very comfortable with identifying these different geometries of different substances. Let's go ahead and work through example number 10. And if you can do this by yourself, go ahead and do that. If you can't, please continue the video. So it starts with their central atom, which is carbon. You draw the dots for your central atom. Usually your central atom is the least electronegative. There are 4 fluorine atoms, and you can tell where the fluorine atoms are going to go. They're going to go around the 4 unpaired electrons that carbon has. Now, fluorine has 7 valence electrons, and once again, I do take this shortcut because I know I'm not going to have to split up those lone pairs. And I make my sigma bonds. And here is CF4, carbon tetrafluoride. Now, carbon tetrafluoride has 4 pairs of electrons around the central atom. So with 4 pairs of electrons repelling each other, what shape will be forming out of that? And the shape that you should say is, in fact, a tetrahedral shape. So 4 electron pairs makes what is called a tetrahedral shape. Let's go ahead and use the next response, which is xenon tetrafluoride. So xenon has 8 valence electrons. You're going, why would xenon, a noble gas, bond with fluorine, 4 fluorines? And that's because xenon is a pretty large noble gas. Lots of energy levels, lots of distance. That means that xenon holds on to its valence electron very, very loosely compared to any other noble gas above it. So what you're going to do, xenon, as long as xenon is attached to a very electronegative atom like fluorine here, that electronegative atom is going to pull xenon's electron more towards it, but they're still sharing once again. And remember, xenon can have an expanded octet. So I'm going to start bonding, and what I'm going to do when I bond is I'm going to see if I can make sure I allow the lone pairs to pair up together and close enough to pair it together. If you erase, you're more than welcome to do that. So if you look at this structure, I have a total of 1, 2, 3, 4, 5, 6 electron pairs around the central atom. That is an octahedral shape. However, 2 of them are lone pairs. So when you think of an octahedral shape with 2 which are lone pairs, I am ending up with a trigonal planar shape. Or sorry, a square planar shape. So I see my square coming off of this, and I'm going to use my yellow marker. So here's my square. So this is going to be a square planar shape. All right, now we go to the next one, ClF3. So Cl has 7 valence electrons. Fluorine, once again, has 7. And I know that we're probably not going to divide or use the lone pairs, like separate them in any way. And so I'm going to put the next fluorine over here. So here I see my attachment, my sigma bonds. And so I see a total of 1, 2, 3, 4, 5 electron pairs around the central atom. With 5 electron pairs around the central atom, 2 of which, by the way, 5 means it's trigonal bipyramidal, 2 of which are lone pairs. What I'm imagining is a T shape. So you're going to see a T coming off of this shape right here. So the answer to this is T-shaped. You can ignore the answers about hybridization for now. You can let it Ignore it for now until we learn about hybridization. So ignore anything that describes hybridization until we actually learn about it. Polar substances or covalent compounds display polarity. And what polarity is charge distribution within the structure. It depends on two factors. The bond polarity using your dipoles, recall that dipole moments are based on unequal sharing between atoms. And then it's also dependent on molecular geometry. So let's go ahead and look at these two examples here. If I have a polar molecule, usually means it's polarizable. And that means there's charges distributed unevenly in this structure. So a polar molecule will have a net dipole as the shared electrons spend more time around atoms with higher electronegativity, where we symbolically represent with this partial negative, and away from the lesser electronegative atom, which has a partial positive. Usually a polar molecule is asymmetrical. So let's look at it, water. Now once again, we need the geometry to understand why water is polar in the end. So here we have water, drawn out Lewis structure. The electrons that are shared between the oxygen and the hydrogens are shared unequally. Oxygen is more electronegative than hydrogen, so the electrons are going to flow more towards the oxygen, making oxygen partially negative and the hydrogen partially positive. Likewise, right here in this bond, you're seeing the oxygen be more negative, partially negative than the hydrogen. So we're looking at each bond and how the electrons are shared between the two atoms that are bonded. So this is called a dipole. The arrow always points towards the more negative, leaving us a tail that looks like a positive sign. That positive sign means this side is more partially positive. So this is called a dipole between as far as the pull of electrons. Now with the dipole, if you think about it, that means that electrons are really being pulled towards the oxygen. So the overall dipole, the net dipole, is towards oxygen. How we represent the net dipole going towards oxygen is just making a really big dipole towards oxygen. By the way, there is a little error in this structure, not little, but there should be a lone pair also, giving oxygen an octet. But the shape and geometry of this structure, meaning since this structure is bent, we know it's bent, this is what creates this unequal dipole, or the net dipole. This is what creates a net dipole. If the structure were linear, so I'm going to propose a scenario where, say, water was linear rather than bent. If water were linear rather than bent, your structure would look like this. So this would be nonsensical, of course, but say the structure was linear without the two lone pairs that you see around the oxygen. Now, as a linear structure, your dipoles are still existing because the oxygen is more electronegative than the hydrogen. So for both bonds, you're seeing the electrons being pulled towards the oxygen. But notice how the electrons being pulled this way is going to be opposed by the electrons being pulled the opposite direction. So there's no net dipole. In other words, as far as the dipole, there's zero net dipole. And this creates what is called a nonpolar structure. So the fact that this structure is bent, this is why this is a polar structure, whereas this is nonpolar. The fact that it's linear. So the geometry plays a very key role in the polarity of a structure. So the molecular geometry makes this structure be asymmetrical. The bent structure is asymmetrical, as opposed to the linear structure, which is symmetrical. And that's why the dipoles can cancel each other out. Whereas if it's asymmetrical and bent like this, the dipoles do not cancel each other out, and you're seeing a net dipole going towards the oxygen. Now let's look at an example of nonpolar. Nonpolar covalent molecules do not have a net dipole, as the shared electrons spend equal time around both atoms, usually, or all the atoms, usually symmetrical. Note, hydrocarbons made up of carbon and hydrogens are nonpolar, since their carbon-hydrogen bonds have electronegativity difference of 0.4, which is closer to a nonpolar bond. So this is a little bit of a fact. Hydrocarbon CH bonds are always nonpolar. Here is an example of a nonpolar molecule, and let's explore the dipoles that are on this nonpolar molecule. It's CH4, and the structure or the geometry of this substance, CH4, is a tetrahedral. So the geometry is really important because it makes this structure symmetrical or asymmetrical. But this structure looks symmetrical to you and I. If we draw a line of symmetry along the bonds, you'll see that that line of, or that plane of symmetry, if we drew a plane of symmetry, you'll see that, like if I drew it along this bond right here, plane of symmetry, I'll see that the structure is symmetrical. Even whatever I see on one side of the plane is a mirror image of the opposite side. So the dipoles are all going towards the carbon. It's a very weak dipole, by the way. And notice this is a carbon-hydrogen structure, or bonds. And so these bonds are very weak dipoles. The structure is symmetrical. It's tetrahedral. So there's a net dipole of 0 as a result. 0 net dipole. And because there's a 0 net dipole, that means the structure is nonpolar. That's why symmetrical structures oftentimes are nonpolar, because their net dipole is oftentimes 0. What we're going to do is we're going to draw 3 molecules, and we're going to draw the dipoles for the bonds, and then we're also going to determine the geometry, and from there we're going to be able to determine the polarity from that, okay? So let's start off with carbon dioxide. Once again, central atom. At this point in the game, you should be feeling pretty comfortable and good about your drawing your structures. Your Lewis structures, that is. I'm out of room over here, so just know that there's a line over there on that side. Okay, so I'm going to single bond first, and then I realize that there are double bonds. So this is carbon dioxide class. Let's draw the dipole in. We're going to draw it in black so we can contrast the colors. The electrons are being pulled towards the more electronegative atom, oxygen in this case. Likewise, the electrons are being pulled towards the oxygen. This is a linear structure. And so if you think about the dipole going this way and then the other opposite way, they cancel each other out, these two dipoles. So this structure is symmetrical and it's nonpolar. So I'm going to emphasize it. I'm going to look at the symmetry to help me also to determine the polarity. So symmetrical and nonpolar. Ammonia. Let's go ahead and take a look at ammonia. Nitrogen, 5 valence electrons, 3 hydrogens. Bond them together. And then the geometry here is in fact a trigonal pyramidal shape. And it's asymmetrical. So I'm actually seeing the asymmetry. And the bond polarities, once again, drawing the bond polarity, the electrons are being pulled towards the nitrogen, probably more it's going to be more electronegative here. And it looks like in the trigonal pyramidal shape, all the electrons are going towards the apex of the pyramid. So that means there's a net dipole. And the net dipole, making it in yellow, is in fact upward towards the nitrogen. This is 0, by the way. I should have written it in. And because there's a net dipole, this substance is polar. Let's go to the next structure. The next structure is called Methylene Dichloride. Carbon in the center. Hydrogens. And then chlorine. 7 valence electrons. Bond. And so now you have your geometry. The geometry is a tetrahedral shape. The structure is asymmetrical, and I'll tell you why it's asymmetrical. It's asymmetrical because now if you drew a line of symmetry in through any of the bonds, so I'll draw it through it, and remember this is tetrahedral. So if I drew a line of symmetry through this bond here, I know it doesn't look like a line of symmetry, but you have to imagine this to be three-dimensional. Your structure is actually asymmetrical. So that means this structure is in fact polar. Best to build it three-dimensionally. And you can see that it's also asymmetrical by the fact that there are different bonds. There's chlorine here and hydrogen, so that you're not seeing the same atoms bonded to the central atom. So you can actually see the asymmetry from that. Where is the polarity? It's actually going to be towards, let's do the dipoles so we can see where the polarity or where the net dipole is. So there's a very weak dipole towards the carbon, very weak. So I'm going to draw little dipoles because it's weak. But there's a very strong dipole going towards the chlorine. So the net dipole is going to go towards the chlorine atoms, however directed the chlorine atoms. So if the chlorine atoms are positioned downward, then the net dipole is going to go downward towards the chlorine atoms. So it's really towards chlorine atoms. There are 4 types of intermolecular forces that we will see in covalent compounds. These are the forces that are in between these molecules. The 4 types, and it goes from weak to strong. So the first one is London dispersion, and then it goes into dipole-dipole, and then hydrogen bonding, and then ion dipole. These are the types of substances that you will see having these forces of attraction. And you'll notice that as the substances get stronger charges, or you will see, or there's higher or stronger charges, you're going to see stronger forces. And that is Coulomb's law in essence. The higher the charge, the stronger the force of attraction. And these words right here will make it very prominent to understand why the charge is getting stronger as you go across here. So let's talk about London dispersion forces. It occurs in noble gases and nonpolar substances. It is created by what is called temporary dipoles. And the more volume, the more electrons, the stronger the London dispersion. We'll talk about this in light of this modeling. London dispersion forces occur when you have an atom or a molecule where the electrons are shifted to one side of that atom. So this is a hard model to see that, but the electrons are shifted over to the left side of this atom, creating a dipole, a partial negative charge on this side and a partial positive side on this side. And that induces another of the same atom to basically have a negative charge on this side as well, partially negative, and then a partial positive on the opposite as well. And so this continually happens, and it only happens very instantaneously and temporarily, and that's why this is called a temporary dipole. So this shifting, this dipole that you're seeing, and I'm going to draw it in light of an arrow, is going to occur very momentarily. And it's only because of the electron shifting to one side in that instant that these dispersion forces will occur. And once again, the way we represent dispersion forces is we draw these dotted lines to represent the attraction between these opposite charged forces. I'll make that a little bit more obvious to you. So we're going to represent there. And the attraction occurs from the fact that this side is positively charged, this side is negatively charged, and so these two particles are going to attract each other through opposite attraction, opposite charged attraction. Now, because these electrons are shifted to one side momentarily, that's why it's called a temporary dipole. So the electrons will shift back to distribute in an atom or a molecule. The next one, dipole-dipole. Oh, by the way, so sorry. The more electrons you have, what happens is the stronger these charges, these partial charges will be. So that means this will be even more positive, this will be more negative, so there's going to be a stronger attraction because there are more electrons causing a more partial positive, partial negative and a partial positive charge. Now we go to dipole-dipole force. This occurs to polar molecules, and this is a permanent dipole that's occurring between substances. In other words, the dipole moment that I'm going to represent is an actual dipole, like this, towards the chlorine. The chlorine's more electronegative in HCl. When that happens, because of the permanence of this dipole that's created from the sharing of these shared electrons between hydrogen and chlorine, this chlorine being more electronegative is going to hold the hydrogen's electron more towards its nuclei, creating that permanent dipole. Now, with that, if you have an adjacent molecule whose side is opposite in charge, in other words, partial negative attracted to partial positive, so there's going to be what are called dipole-dipole forces. This is a dipole-dipole force between the substances. Hydrogen bonding. Hydrogen bonding occurs because hydrogen is bonded to a very electronegative atom. And that very electronegative atom creates an even stronger dipole towards that very electronegative atom. And so this deep, strong dipole is a stronger charge, partial charge, and thus the attraction between opposite charges on adjacent molecules, between molecules, will be what makes this force very strong, because you're looking at a very polar molecule attracted to another the same polar molecule, and it's because of their strong dipoles that you're seeing, their strong permanent dipoles, that you're seeing this strength of attraction between these particles. Ion dipole is even stronger because you're looking at an ion with a polar molecule. The ion has a full charge to it, and it's attracted to a polar molecule which has partial charges. And so here you see chloride attracted to the hydrogen end of water, which is positive, partially positive. The ion in itself is a negative ion. Now, if it's not clear, I'm going to write that in so you can see this is a negative ion, whereas this one's a positive ion. Negative versus positive ion. And notice how the positive ion is going to have the oxygen end of water because oxygen is partially negative. Negative end of water is attracted to the positive charge ion. Now, it takes a lot of water molecules to pull off each of these ions. So note that this is still an intermolecular force, and it is the strongest of the intermolecular force, but nonetheless, it's still an intermolecular force, which means it's a weaker force than the intra that would occur between the two cations and anions in the ionic bonding that is here. Okay. Now, example 12. I would like for you to do this on your own, given these four different forces. I'd like you to think through it, understand the different types of inter forces compared to the strength of the intra forces, and really be able to label what you need to label here, and then understand just the conceptual part of why one has a higher amount of energy than the other. So, please make sure you're working through example 12. The answer key is at the very tail end, but work through it very carefully. Continue on with example 12 in light of what we've covered so far. Please make sure you're applying your understanding using this evidence that you see here. Just think it has to be something to deal with intermolecular forces as you go through this. Following through all the way to the end. Your answer is down below. Please check your answer as you go through this. Model what you can model. It's really important to be able to model the interactions. Let's get into hybridization theory. Hybridization theory arises from exploring substances and looking at how much energy is required to break their bonds. We discovered that the bonds that occur around a central atom oftentimes were equal in energy, and how that could be possible is because of the mixing of atomic orbitals in an atom. And the mixing, the hybridization, actually generated a new set of hybrid orbitals called sp, sp3, sp, or sp2, sp3, sp3d, and then so on and so forth. And they're occupied by valence electrons that are shared between the atoms. Hybridization occurs because central atom treats each bond formation equally as equivalent hybrid orbitals, resulting from a covalent bond. It's important when you're counting hybrid orbitals that you're counting the central atoms, bonding pairs of electrons, and non-bonding pairs of electrons, which are also called lone pairs. Pi electrons do not occupy hybrid orbitals. So how does hybridization occur? How it occurs is this. So we studied molecules like BCl2 here, beryllium dichloride. And when we studied beryllium, specifically beryllium because beryllium is the central atom bonded to two chlorine atoms, we looked at the orbital notation, which right here is represented. And we said if this was true, this would be what the electron dot would be. But it's not true. How could that be possible for beryllium to bond with two other atoms if this electron is paired? So we have to have a better way to understand how this bonding could take place in beryllium dichloride. And so what we do is we actually hybridize orbitals, the s and the p, together. Upon hybridizing, what we're doing is we're taking one electron, moving it to one of the p's, and merging them together. So merging them together will give you sp. And then now you have two unpaired electrons, which align with exactly what you see here, two unpaired electrons. And this actually helps us to understand the bonding that takes place between the two chlorine atoms and beryllium. Let's look at sp2. sp2, here I'm looking at a structure. This is the structure I'm looking at, and I'm looking at carbon and understanding how carbon is able to make these bonds that you see here. One to carbon and two to hydrogens. And then we also see a pi bond. So there's also a pi bond in here that we have to account for. So I wanted to use this as an example of how we have an unhybridized pi orbital. So here, once again, if we were to keep the regular quantum model, this is what we would see as far as electron dot. We would see a paired electron, paired like this, and we would see two unpaired electrons like you see here. But this is truly not how carbon bonds. Carbon bonds with this in mind, 4 unpaired electrons. Now, how this is going to happen is we're going to need 3 hybrid orbitals. And so I'm going to take one electron and move it over, move it over to the p orbital. And then I'm only going to hybridize one of the s and 2 of the p's. And in doing so, now I have what is called sp2 hybridized orbitals, because I took one s and I took 2 p's. The other orbital is actually an unhybridized p orbital. And so this doesn't hybridize with the sp here. It doesn't combine. That's why it's separated with a gap here, because this is actually considered an unhybridized orbital. And of course, here are hybrid orbitals. And with that, we see the 4 unpaired electron, one that's unhybridized, which is where the pi bond will occur, and the other 3 is where your sigma bonds will be for the carbon and 2 of the hydrogens that will bond. To evaluate that substance, the substance that we saw earlier, and I'll redraw that substance. It's a double bond right here. I'd like to describe what's happening in this model here. So the red represents the hybridized orbitals. So here you have 2 carbons. These are the 2 carbon nuclei in the center. And so this is the bond that's occurring between 2 carbons on a hybridized orbital. Here I see another bond right here on a with hydrogen on a hybridized orbital, and then another bond over in the back here on a hybridized orbital. Same over here and here. Now, what are these 2 here? This is actually the 2p orbital that's unhybridized. And so what you're going to have is an electron on one atom. So say there's an electron here, and then an electron here, and they will engage in what is called a pi bond. So this is your pi bond on an unhybridized orbital. And this explanation helps us to really understand it. So each carbon's orbital notation only shows, it basically describes the hybridization and why the pi electron is occupied on an unhybridized 2p orbital, just as I stated up here. Let's go to sp3. sp3 is very indicative of this shape called tetrahedral. And again, here's a typical substance that has sp3. Once again, carbon, if you were to look at the central atom and its orbital notation, you wouldn't see that carbon really align well with the bonding that takes place in this substance here. So we hybridize, and when we hybridize, we move an electron over to here. I'll show that. Move an electron over to here on another empty orbital, and then now we mix the s and the p together. Notice we're mixing one of the s and 3 of the p's, thus it's called s1 p3, and that will be your 4 unpaired electron on sp3 hybridized orbitals. So this is your bonding. This really does align with the bonding that takes place in this substance here. Hybridization theory helps us to understand bonding and how the bonding leads to equal energy bonds between carbon and all 4 hydrogens. Okay, so now we get to PCl5. How do we create this structure? Well, this orbital notation actually does not do it. It actually shows a paired electron and three unpaired electrons. But notice that we need all four or all five of these to be unpaired for this to happen. So one of the electrons will jump over to this D location, this empty D location, and thus we have one S, one, two, three P's, and one D. So sp3d. And remember, if there's no number, it means it's 1. So that's why we have 1s always, max 3 P's, and then of course we can go all the way to D5 if we wanted to, but of course we don't need to. We only need one of the D's to hybridize. And as a result, I have 5 unpaired electrons that looks like this, and that's the nature of the bonding that occurs in PCl5, which is phosphorus pentachloride. Let's look at sulfur. Sulfur central atom has 6 bonds right here. How does this explain it? It actually doesn't, nor does this explain it. So we're going to need to hybridize. And what we're going to do is we're going to hybridize d orbitals. And I didn't write that in, but I'd like to write that in right now for you to see. So we're going to hybridize. There's 5 d orbitals. So one electron's going to go over here, another electron's going to go over here. So it looks like we're going to hybridize one s, so here's an s orbital, 3 of the p's, and 2 of the d's. And so this is called sp3d2. And notice how this truly does align with the bonding that takes place right here in sulfur hexafluoride. So what I want to do is I would like to work through some of these example problems with you and then let you on your own. So the big question is, how do we put this into play? How do we figure out hybridization? So ultimately, hybridization, to count your hybridized orbitals, is to count how many electron pairs are around the central atom. So if you look at sulfur here, I need 1, 2, 3, 4, 5, 6 pairs of electrons. Thus, I need 6 orbitals. The first orbital I would hybridize is the s, 3 of the p's, and 2 of the d's. That will give me 6 hybridized orbitals. And so the key is just to count around the central atom how many you need, and then that will tell us how many hybridized orbitals you need. Now, lone pairs will take on hybridized orbitals. So if there's a lone pair in this structure, understand that it will be on a hybridized orbitals, those lone pairs. And they will be paired up in itself. So a lone pair would look like this with a paired electron at one of the spots. So let's take a look. Nitrogen. The first thing you want to do is draw the structure, the Lewis structure. That way you can, this is what I mean by you'll get good at it. After this many times drawing the Lewis structure, you'll get very good at it. So here's my central atom, bonded atoms. Sorry, I should do all the dots, but then I get so comfortable at one point where it's just really easy for me to connect and know where the connections are. So how many hybridized orbitals do I need? I need 1 here, 2, 3, and 4. So this lone pair will take on the 4th hybridized orbital, which means I'm going to hybridize 1 of the s and then 3 of the p's. That will give me 4 total hybridized orbitals. And what this looks like, if you want to be very technical, I'm going to show you what that looks like. I'm going to erase the sp3 for a second so I can show what the sp3 hybridized orbitals look like. So it would be 1, 2, 3, 4, 4, and this would be called sp3. And of course, 3 of these will be unpaired for hydrogen to bond, each of the hydrogens to bond there. And then one of them is going to be paired up. Now, you can put that paired up in the back if you want, or the front. It doesn't matter, or even in the middle. Just ultimately, these are equal energy orbitals that are hybridized, and they're called sp3. And this is where the lone pair is right here. And I will make a remark on that just so that you can be clear. This is the lone pair. Or I should even put an arrow. This is the lone pair. Let's go to B. In B, once again, draw the Lewis structure. Okay, I'm going to do 3 fluorine atoms. Now, I'm going to put them right here. One of the fluorine atoms, and then I'm going to try to get the other one to bond with the other unpaired electron. So here's right here. So here you go. Here's your sigma bonds. How many unhybridized orbitals do I need? I need 1 here, 2, 3. So the 3 fluorine atoms will bond to take on the 3 unhybridized orbitals, and then 4, and then 5. So I need 5 hybridized orbitals, which means my hybridization is going to be sp3. So that's 4 hybridized orbitals. That's 6. So D1. So S1, P3, D1. You don't need the ones there. You can just say sp3D. Now let's look at the next one. Arsenic pentafluoride. So around arsenic, there's 5 valence electrons, and I know that each one will be bonded to each of the fluorine atoms. And I like to take my shortcut, but I will not forget the lone pairs around the fluorine atoms. That's a very common mistake among students. They take such quick shortcuts that they want to get through this structure building, and they don't do all the valence, they don't represent all the valence electrons for all the atoms. So here's my sigma bond. And so the question is, how many hybridized orbitals do I need? It looks like I need 1, 2, 3, 4, 5. So I need 5 orbitals to be hybridized. And so that's sp3, which is 4 right now, and then D. So sp4, notice how the shape and geometry of these two shapes, the rooted shape is actually the same shape, which is trigonal bipyramidal. They both have the same hybridization, which means they both have the same geometry, trigonal bipyramidal. Carbonate ion, same thing. Draw the Lewis structure. And I do recall that the carbonate ion has 2 added electrons to the structure, and it's probably going to go on the oxygens, okay? All right, so I'm going to swap something because I see something else, or I see a multiple bond, so I'm going to swap these two. Okay, I'm going to add an electron to the structure. Oh wait, sorry, I'm going to first sigma bond. So I do my first initial sigma bond. And then I add my electron to the structure. I'm going to add it right here to this oxygen carrying a formal charge of -1. I'm going to add it also to this oxygen carrying a formal charge of -1. And then, of course, I see a double bond possible because I see that carbon lacks 8 electrons. It has 7, and this oxygen also has 7. So when we're deficient, it's best to share together. And that's what you're going to see, an extra bond, or a pi bond. This structure has a 2 negative charge overall. Hopefully you can add up those negative charges. -1 plus -1 gives you -2. I normally, with a polyatomic ion, I normally put brackets around the structure. And then I put the 2 negative charge on the outside. There. Now, but that's not the point. The point is understanding what kind of hybridization we're looking at. So let's count the hybridized orbitals. Pi electrons do not count. They're not on hybridized orbitals like we see in this substance right here. So look in the previous page of your notes. You'll see that pi electrons are an unhybridized orbital. So you're going to need one hybridized orbital right here, another one, and another one. So you only need 3 hybridized orbitals. With 3 hybridized orbitals, that would be including sp2. So you need one s and 2 p's to make 3 hybridized orbitals. Now think about this for a second. If it's sp2, I know it's trigonal planar in shape. And notice this is a trigonal planar shape. Once again, the pi electrons do not they don't repel anymore to create a different geometric shape. Let's go to the next. Tellurium hexafluoride. Sorry, I'm just coordinating, making sure I'm writing in the same color. So tellurium has 6 valence electrons, but there's 6 fluorine. And I'm going to take my shortcut, 7 valence electrons. You're going to like this shortcut more and more, I'm thinking, because it makes it faster. Okay, I'm ready for my sigma bonds. I've oriented all the bonds really nicely so that I can do my sigma bonds. And so how many hybridized orbitals do I need? I need 1, 2, 3, 4, 5, 6. 6 hybridized orbitals would mean I would need to hybridize 1 s, 3 p's, and 2 d's. That's a total 6 orbitals hybridized. Let's do the last one. The last one is sulfate ion. By the way, always pause if you find yourself pretty comfortable with this and try to do it before you see me doing it. That way you can practice on your own. Just watching me do this is not going to help you. Doing it yourself is going to help you. So there are 3 oxygens. Okay. The 3 oxygens, one of them, or 2 of them are going to gain 2 electrons. And again, I'm always checking to see if there's any added electrons. So you're going to add 2 E minus, okay, to the structure. So let's first sigma bond and then we'll add it afterwards. I'm going to do my first sigma bond. And then I'm going to add. And where I'm going to add, I'm going to save this one for a possible double bond if I need to. And then, but I'm going to add it to these 2 atoms. So adding 2 electrons. Here's one carrying a formal charge of -1. Here's another one carrying a formal charge of -1. And that will then make the 2 negative charge be accounted for. And so I look at this structure and I count my octets really quick. There's 7 here, and there's actually 2, 4, 6, 8, 9 here. So 9 is what is way too much. And then you're going, why don't we just transfer this electron over, Mrs. No? Well, that would cause all the atoms in the structure to have a formal charge, and that is not good. So your best bet is to have an expanded octet for sulfur. In other words, making a multiple bond out of here, allowing sulfur to have, making sulfur have what is called, or letting it have 10 electrons around the central atom. And sulfur can expand its octet because it has room to do that. Oxygen has an octet, so we're good to go. This is the most stable, best structure. Once again, we're always trying to make sure we minimize formal charge, and to have every single atom have formal charge is not really working towards minimizing formal charge. Okay? So my structure got cut off of my diagram, so I just drew it in here. Yours should be there. I labeled this C1, so this is the C1. It's asking for the hybridization around each of the atoms. Again, I'm going to really go through how many hybridized orbitals I'm going to need around each of these carbons that you see here, right here, C1 through C4. So if I were to literally draw this structure out carefully, you would see 3 hydrogens. This is what the 3 hydrogens looks like. So how many hybridized orbitals do I need? It looks like I need 1, 2, 3, 4. I need 4 hybridized orbitals, so it looks to be the answer for C1 is sp3. That's what 4 hybridized orbitals are, 1 s and 3 p's. Now we look at the next one. In the center of the carbon 2, I need 1, 2, and 3. I don't count the pi electrons. They're on unhybridized orbitals. So I really only need 3 hybridized orbitals here. So this is going to be sp2. Then we go to the next. I look to see that I need 1 here. Don't discount the pi electrons. Eliminate it. Discount it altogether. So you're going to need 1, 2, 3. So it's sp2 hybridized orbitals. This last one, the last one is, once again, I see a pi electron. The sigma is going to be where the hybridized orbital will be on, and then so that's 1, 2, 3. So the last one is sp2 as well. Now notice how all around the sp2 hybridized orbitals you see, you see a very, very distinct geometry. sp2 means that the geometric shape is trigonal planar. sp3 means it is tetrahedral. All right, this is all you now. I'd like you to really practice example 14 and example 15. Do your best to take everything you've learned in this unit and pull it together in these conceptual questions. And also work through example 16, moving on to check your answers at the very end. So please make sure you're really working through the problem and checking your answers on the very tail end. And this ends covalent compounds and this whole unit of chemical bonding. Don't forget to go back to the first page, look at the concept map, and see if you truly do understand all the 4 types of bonds: ionic, metallic, covalent network, and covalent. And really study that chart, because the chart on that page, I believe it was on page number 2. Yes, 2. That chart on page 2 leading into page 3 is a very good comprehensive view of this whole unit. So review it.